we're Futurescape. We're a distributor of Ansys products here up in Canada. And we are going to present myself and Ali, who's the application engineer, electronics cooling benefits of using Ansys Discovery. And so I'm going to show a quick PowerPoint presentation, kind of giving an overview, and then after that, Ollie's going to take over and actually showcase the software and show you a workflow with a specific application. So let's get right into it. Some of you have maybe done simulation or analysis, either maybe electrical analysis, mechanical analysis, RF analysis. And some of you maybe have done some design, possibly doing product design, building design, different types of design in different forms of 2D or 3D applications. There's always been a bit of a barrier between the designers and the simulation analysts because usually there are two different types of tool sets. There's been some integrations with some of the design tools, but generally speaking, when we're moving into validation, there's usually a bit of a bottleneck. So where is that bottleneck occurring? It's usually at the beginning of the design. Usually the designer will want to come up with different concepts, to be able to try different scenarios for trying to meet the requirements for say an electronics application. And there's a lot of different things to consider: the functionality, the maintainability, the different environmental requirements, electronics optimization, thermal management, etc. And so a lot of those different requirements need to be conceptualized. So you might be able to come up with maybe 4 or 5 different concepts and then finally select on one and move forward. But the problem is usually the testing and simulation is done afterwards, which sometimes could be done up front, but a lot of times the designers, the engineers do not have the skill set or the time to be able to do that. So how can we empower the engineers to be able to do, designers and the engineers to do simulation up front? That's the whole point, is to try to bring some of that simulation work that's not necessarily the highest accuracy, but the speed in which performing that simulation, so there's not a huge cost barrier to get into that conceptual design simulation. So where does Discovery come in to help with that? What we have here in Discovery is a geometry prep tool. Basically, it's a CAD modeling tool. What's the advantage between Discovery modeling versus other types of modeling is the modeling inside Discovery is extremely flexible. It doesn't have a history tree. It's a direct modeling system, so you're able to make very radical changes to try different types of scenarios right inside the tool, and you don't necessarily need to commit to that geometry. It's just being used to conceptualize some of the simulation, and then after that, you can, right in the environment, do upfront multi-physics simulation. So, for example, we have RF simulation, vibration simulation, thermal simulation, all within the same environment, so that way you can test that concept before you move forward to detailed design. Now we're going to move forward. What's the workflow? The idea behind the workflow of Ansys Discovery is you would start off with a basic design that you might have come up with. Maybe you brought that in from one of your design packages, such as Creo or SolidWorks or CATIA, and you would bring that into Discovery because you're able to model inside Discovery any form of imported geometry because it's a direct modeling system. So in there, you're able to actually do different types of modeling, different types of scripts, and then you can do quick setups for doing simulation results. So you can do fluid simulation, thermal simulation, RF simulation, etc. And you're able to do that, get those results within seconds because we're using GPU solvers right in the environment. And then you can modify, you can repeat that step again and go in and modify that geometry inside the environment to optimize that topology for all of your different requirements. So what are the 5 key differentiators with Ansys? First of all, it's just work simulation. When you're bringing the simulation in, you don't have to worry about convergence problems. It has a lot of relaxation characteristics when it comes to the meshing and and the simulation results in the background. So you don't have to worry about like being a simulation expert. You can just go in and just do quick setups, and then it'll just give you quick results on what you're setting up. It leverages all of the Ansys solvers in the background, so it's quite accurate relative to other solvers out there. But that being said, it's not meant to replace the higher end simulation tools. You can do quick geometry changes during the simulation as well. And this is a very advantageous, again, because you're able to do conceptual design right inside the environment and then re-simulate that same geometry with those same setups without having to reapply those parameters. And it has a very easy user interface. I got a very really interesting interface where you can get trained up on the tool relatively quickly. So it's not going to be one of those full-time tools that you need to be on. You can be a casual user of Discovery without actually having to worry about losing the ability to be able to use it. And the thing that's really nice about this is that it's using multi-physics. This really is a true multi-physics tool. So inside the environment, you actually have the ability to test multiple requirements on the same topology. So you don't have to worry about transferring that geometry or prepping that geometry for different types of simulations. You can do that all within one environment and then flip back and forth between the results, so that way you can make determinations on how those changes in the geometry affect your design performance. And as you know, we're connecting to all of the Ansys portfolio in one ecosystem inside the environment. So you're basically connecting to all of the simulation and model prep right inside the environment. So let's talk about electronic cooling specifically. Electronic cooling, we're going to do a performance of a simple electronics enclosure to show you the capability, but then after that we can discuss specific applications. So let's talk about, for example, some of the electronic cooling challenges that are currently emerging in the market. First of all, what we're seeing a lot is we're noticing things are moving towards more mobility platforms, which means we're getting into more autonomy, like machine learning platforms, control optimization platforms, AI platforms, and we're looking at like high peak battery management and GPUs inside those applications. What does that mean? It means very high thermal flux on the die, transfer materials right onto the chip. So, a long time ago, this dates me, but, many years ago, it used to be multiple chips you used to have to worry about. Now they're really increasing the thermals, the thermals right into one or two locations, and it really is has to be optimized right from the die right up. So once we connect right to the die, usually like using transitional materials and whatnot, we're moving it to fin cooling optimization, thermal spreader plates, heat pipe optimization, and some of that can be very complicated because a lot of the times when you're doing high performance applications, off the shelf components are not necessarily going to be satisfactory. The thing that's most important about electronic cooling is we're talking about a multidisciplinary team. So your placement of those components and communicating the placement and management of the components is actually going to affect dramatically other team members that you're dealing with. So for example, you might be dealing with your RF people, your electronics layout, your testers, your mechanical team, your software teams, and you're dealing with multiple people that are being impacted by your design. So it's very important to make good decisions up front, because once you hit detailed design, it's not just the labor workload of the thermal team or the mechanical team, it's affecting everyone else around you. So making those upfront decisions quickly is very important before you make commitments to the overall design concept. What we're going to talk about today is we're going to talk about bringing that product life cycle back into the designer's hands and communicating with the simulation experts, so that way the simulation experts are doing more of that high-end validation and they're not doing a lot of that churn and getting pressure for doing quick results in their high-end tools. So I'm going to stop right here for the time being, and I'm going to let Ali take over, and Ali's actually going to showcase the tool itself and show a quick application, and then we can go after that application and get into some Q&A. If you guys have any questions you want to ask us after about specific application you guys have, you guys are welcome to put that in the chat, and Artie will take those questions and we'll answer them after, or you could also ask them verbally live as well. Okay, thanks. Ollie, I'll let you take over.
Thank you very much, Ben. That was an awesome presentation. So I'll just quickly go ahead and share my screen. So please let me know once you see it.
Yeah, we can see it.
Wonderful. Thank you very much, Ben. So welcome everyone. This side, Ali. I'm a lead application engineer here at Futurescape. Now herein, we'll be running a very basic simulation of an electronic enclosure, wherein initially we'll see how is our electronic enclosure performing in a normal environment without having any forced convection. And then we'll try to see if we make any design changes in the initial stages, how's the performance varying, right? And as this is the conceptual stage of the design, we have multiple parameters that we can play around with. So we can see how and what fits well with our product at this point in time, right? As you can see in here, let's say I have an electronics component and I'm not much aware about the simulation and all. And at a first glance, for me, as let's say I am a designer, so in that case I might be scared of the simulation and all those kind of jargons that typical basically simulation experts use, right? And I'm in the initial stage of designing my basically electronic enclosure, and I want to know from the very basic idea how I can manipulate my design on the very initial stage so that I have the optimum results as we refine down our design following this, right? So I have inserted a electronic enclosure in here which have the heat sink and all those kind of stuff. So let me just show you, let me hide the enclosure. So here you have the heat sinks and different chips out here, right? Now my first aim would be to get how's the thermal performance of this very arrangement that we have out here, right? So instead of using basic maths, I just jump to the Ansys Discovery and create my boundary condition. Basically, boundary condition is what kind of loads the part is bearing. In this case, it will be thermal loads, right? So I just go to the solid thermal in here and apply heat because all these chips will be generating heat. I'll be applying it all around, and then we'll be having a thermal simulation. Post that, we'll have a initially we'll have just convective transfer, heat transfer. Then we'll see if we have some kind of a fan, the forced convection, how does that improve the performance of our parts, right? Now uh, let's jump into the demonstration. So I have different chips in here. Now the very first thing that I need to do in here is to apply the material, right? So let's say my base plate that we have, I just triple click and I have the option from the library to select the kind of material that I have in here, right? So if it's silicon or if it's something else, I have an option, or I can select from different options, or I can edit and create my own as well, right? Let's say it's PCB laminate. I just select this one. We are good. Now let me apply for the different chips. I select all the chipsets in here or IGBTs, and now in here I can select what kind of, again, the metal that we have, right? So let's say for this we are using silica and we have it in here. I just apply. Now for heat sink, let's say it's aluminum maybe, and for the board as well, let me assign aluminum. Great. So now we are good to move on to the very next step. We have designated the material of all the components in here. Now quickly go ahead and set up a boundary condition, basically the real life loading scenario. In this case it will be thermal loads. Just go in here and we have different options. Based on our application, first of all, I'll need to apply heat because the heat is getting generated from these IGBTs. Click on heat, it will give me option to select the surface or a volume. I selected this IGBT and let's say this one is generating 1 watts of power, right? Similarly, I can apply for different IGBTs in here. Let's say this one is about 1.25. The main chipset that we have is generating about 10 watts. And this one may be, let's say, 2 watts, right? Now herein we have multiple chips which are quite similar. So I can just select them all at once and apply them, let's say 4 watts. Now these 4 watts will be divided into each one of them, so it will be 1 watt per IGBT. Now that's it. Now I have created my boundary condition. In this case, this will be the boundary conditions, and I'm good to start to solve. I just click on the solve button. It will go on and try to simulate the results out in here. And it have already solved for my case, right? Let me hide the enclosure for now. So I can see what kind of temperature variation is there over here, right? I can see in here the maximum temperature is going 107 degrees, which is not desirable, of course, right? But again, it's the initial stage, we can refine a bit more. So within seconds, I have the basics results out in here. We have the contours, right? So let me do the highest values. So as you can see, this chipset is bearing the highest temperature. Now if I just want to have surfaces with the maximum temperature, I can apply in here, let's say 107. So it will give me all the temperatures which are at that range, right? So let's say if I apply 70, it will show me all the 70s. I can move the slider and see how the temperature variation is. As might expected, as I move to the right, temperature will increase. It's mainly on that chipset, right? Now let's say I need to alter my design, right? Let's say this chipset I might have accidentally put, or I need to change something. So I just put it in here, enter, and the software automatically recognizes that I made changes and it will go ahead and again simulate, and I can now again see the results how it's been, right? Similarly for different chipsets, I can just apply from here, and while I'm just changing things up, it will show me the results out in here, right? Now coming on to the different things. So again, in here we haven't created any sort of a mesh, right? What if my results might not be that accurate, because it's explore mode in which we are exploring the design, so the results will not be that much accurate. So I can see the resolution of the simulation that I am having, or the mesh. Basically it's called voxels that's being created in here. I might see that it's not that good, right? I can see the size of these voxels. So instead of creating mesh, Ansys Discovery divide the volume in these cubical voxels on which the equations are solved. Now based on my GPU capabilities, I can refine it. Let's say I just want to refine these, right? So I can just, in the explore region, I have bottom in here to enhance my basically fidelity. I move it to the right, and you'll see it will have more and more components. But in that case, basically what will happen, the time duration it will take to solve will be slightly higher. not much, but slightly. As you might see, again we have the results, and we can see how the results have been. See, now we are capturing the real data, right? Initially it was showing us in here the maximum temperature, but now it's showing that, yeah, the main chipset is the one who is creating the max amount of temperature. Now I can see during my refinement how my progress have been and how the temperature is varying during my design iteration or my quality iteration that I'm doing from my end, right? Now let's say this was just the basic, right? I had the idea, I got it. Okay, so this is how, if we do not have force convection, this is how my part is going to behave. Now, what if I want to, see in the case if we have fan or something, how does that changes? Or let's say, how does, if I'm wearing these height of these, how will that change? So what I can do, I can just go in here, select one of these, and within in here we have an option in which I can select similar faces. I can pull it. Let's say I want to have some kind of a parametric involved in here. So let's say I'm doing it for 0.5 mm for now. Now I can have a all kind of parameter that I've set. I can have different variation, right? Now let's say the parameter that I've set is 0.5. Start value, let's say, is 0.5 mm, and I'm going to, let's say, 2.5 mm. And the increment is just, let's say, 0.4. So there will be 6 divisions under which the simulation will be run. I just create 6 defined parameters, and I can just come in here and update all. Now the maximum temperature in each of these will be calculated, and I'll see it over here. It is automatically making the changes in terms of basically the CAD. As I can see over here, this height of these heat sink will automatically get increased with each iteration. So as I might see, at 0.5 increment was 61.3, but increased to 0.9 it becomes 61, and similarly it will vary and show me how these parameter is affecting the results of the maximum temperature. Of course, the heat sink size increase will lead to more heat dissipation, but that might not be optimal. As you might see, we have a space constraint as well, and post this I'll show you how the force convection might help in this case. So we are good, and this is how the results look like. Looks pretty good, right? I'm really fascinated by the way it's solved, right? It's really fast in every sense, right? I can see the temperature variation, how the temperature is varying during each iterations. Now let's go back in here and delete this study, because let's say we are doing something else, and we just go back to our initial design that we had. Now I have the enclosure. Let's say we have force convection. In that case, there will be, let's say, fans in here, and there will be outlet. Now for that, if you understand, for fluid to flow, it needs a volume, and here we do not have that volume, so we can created, and it's really easy. In the prepare tab I can just go, and in this I can just go to volume extract, select the bounding surfaces, and I select the seed face. I can see the inside faces in here, so it looks good. I click the check mark and the volume is created. So if I hide all of these, this is the volume in which the fluid will flow. Looks good, right? So you need not to go back to the CAD and ask a designer to generate it for me, or if I myself am the designer, need not to switch back to my CAD tool. Everything is possible within Discovery interface, right? In terms of CAD manipulation and even any changes that I want. Now let's set up some fans, right? It's really cool. So I just go to the simulation again within the fluid flow. If I just click, and it shows me different boundary conditions in here. Right? I can have fans, can have inlet and outlet. Let me just designate a fan. Click on the surface, and shows me basically what kind of a fan I do need. Right? You can filter them out from the manufacturer point of view as well. But let's say I don't want to do all that stuff. I just want to match fans by area, and it will show me all the fans that matches my area. I just select that, and we are good to go. Now we have different kind of options that we can choose in here, right? So how's the volume flow rate, or if I just want to define via velocity or constant pressure, we have those kind of information. Or I can also have the different information about the fan that I'm just inserting in here. Once I'm good, I click the check mark, and the fan is designated in here. That easy it is, right? Now let's go again and set up the another fan. Let me just paste that for now and click check mark. Now at the back, let's designate an outlet because this will be flowing outwards. So outlet, I'll select these surfaces one by one and click the check mark. Now we are good to start our simulation. But in this case, by default, Discovery takes water as a fluid, but again, fans are running, right? So we need to have air. So just select air, and we are good to start our simulation now. Now before I move on to the simulation, let's say I want to do some kind of basically refinement in my mesh. Again, I can use the explore mode from here to do so, or I can again locally refine the mesh as well. Right? Just go to the local, select in here, just select the surfaces, hide all these, and just select these surfaces. I can designate the value in here. Right, let's say currently it's around 0.5. Let's say 0.4 mm. Right. I'm good to run. I just click on run, and it will go on and now show me some decent results. It will create a mesh of voxels. So it's generating the mesh at this point in time. It's not mesh basically, not the traditional mesh that we have. So this is how it's getting created. You can see how it's working on the inside. And again, within couple of seconds or a minute or two, we'll have our results. You might see the temperature have already dropped. Let me bring on that temperature curve in here. Right, so how we are improving our design in the initial stages. So how crucial, you might understand, right? In the initial stages only we are making the best possible choices, right? So that at the end when we refine our design, we are at the optimal level, right? So the design changes need not to be redone from the very basics. Just on the upper level you can change the design because we already have very close to optimal design in the initial phase itself. Now we are just close to 48 degrees. You might understand where we started. 64. Now it's about 61. Okay, so we have the results right now, right? So you can see in here how the results have varied from 61 to 48. So forced convection really had a significant effect on our design, right? Now let's go ahead because it's fluid flowing, basically air flowing. We have multiple kind of results in here. Now these are the contours. I can see how the temperature, where the temperature is highest. If I just want to have iso surfaces again, surfaces with a constant temperature. Now this is something that's really cool, right? Now it feels like we are having into a simulation. Just hide few of these. Okay, so here we have the fluid flow, right? So I can just increase the thickness, decrease the thickness, or decrease the count. So this is how the fluid is flowing through these regions. Now if I want, I can just take the emitter control. So currently it's over here. I can just select it and move it to see much better results. Just move it anywhere so I can see in here. So where the flow is stagnant, all those kind of information I can get from this emitter, right? We also have particles. So if you just want to simulate the particles, this is how the particles are flowing. Again, I can see the stagnant flow over here. This is how the flow is flowing. So in this, I can understand, right? So if the fan is just in front of the heat sink, it might have a better effects because here most of the air is stagnant. Again, I can change the emitter control and I can move the emitter, let's say in this direction, and see the particle flows. Right? So you can see particle flow is stagnant in this region. So I'll try to optimize that as well. And in here we can see basically the direction field. Change this, let's say I just want in here. So this is how the temperature field is. Looks pretty cool, right? As I mentioned, right? So let's say I just want to move the fan, and you might understand it will be really a lot of work it seems, but that's not the case, right? So what I can do, I can just select these from here and just move it around. Let's say I just want it. Again, I can parameterize this as well. Let's say about 15 mm. Right? Again, the solver will go and run the simulation. Got that idea that I have run some changes. Now let's reflect the results for the same. You can see the contours. So it has started working. Again, first we create the voxels on which the equations are solved. It's completely working on my GPU, right? So the GPU usage, as I can see in the monitor down in here, it's around 86, right? Or 89. CPU is just 30, 35. General flow is there. Started to solve, getting some sort of results. Okay, initially we had 48.2. Let's see if we were able to, by movement of the fan, were we able to basically have a optimized design or much more worse than that. Again, couple of minutes and I'll have the results out. So you might understand how easy it is to simulate within Discovery. With just few clicks, you need to have understanding how the real life situation is and how you can insert that using the boundary conditions that we have in the Discovery. And based on that, you can have good amount of results out in here. Now, as it is solving, just let you know, there's one more thing. Let's say I want much more accurate results and I can give a bit more time as well. In that case, we have something called refine mode. Now within the refine mode, basically the tried and tested Ansys Fluent solver is used. Even in here, the mesh is created as well, right? So I'll have the mesh, I have different kind of settings in terms of what kind of mesh I want, and even I can optimize my mesh as well. So the level of control that I get in the refine mode is much more than the explore mode. And again, it's much more accurate than the explore mode. So if I just give you an idea, explore mode may be around 6-7% accuracy it might lose, but in refine mode you can get that much accurate as well, right? So in here we can have local refinement as well, again in the similar way, and I can just run the simulation. Let me just run. Let's say I just want to create a mesh initially. Just click on the mesh and we'll go and create the mesh in here. Right. So you might understand within Discovery, once you have had played around with multiple design, you can have a much more refined results as well if you want that to happen. Right. The time commitment will be slightly more, but again you need not to worry about different kind of parameters. Mesh and all will already be set. If you want to make some iteration, you can make those from the app itself, from these options itself, right? Splitting mesh. Post this, we will open to question answer session. Please feel free to ask your questions. I have already received some of those in the Q&A section. I'll try to answer those questions. And again, please feel free to reach out to us over email. If you have any questions post this webinar, we'll be there to assist you with the same as well. We're just near the mesh completion. Again, in this, CPU is used. Even we have few settings that you can play around with, right? So within the simulation option, we have different kind of settings, right? So basically how you want to converge your solution, we have different options for that. So if you want much more refining, have much more greater idea, you can just play around with this as well. Okay, so we have the mesh, right? So you can see how this mesh has been. Let me just hide all of these. And you can see the level of refinement that we have, right? Looks good, similar to the mesh that we have already seen. And this will lead us to a better solution in that. All right. So looking forward for your questions. Thank you very much again for joining in. And please send out an email if you have any further question after this as well. Thank you very much.
Yeah, so just to let you guys know, all these done with the presentation. Would love to hear your feedback on what you guys thought, but if you guys have any questions you want to ask related to the presentation, we're opening the floor now. You can either put it in the Q&A chat, or you're welcome to unmute yourself and ask it verbally. So we'll just open the floor for the audience and just see what comes up. We'll just wait for a few minutes, see if anything comes up, and if not, we'll adjourn the meeting. Any questions out there that you guys wanted to ask, or any feedback? We have one question. Is it possible to model thermal grease in the app? So, you know, all these meaning like thermal grease or thermal transitional materials or thermal paste. Like, is it possible to actually put in some form of a transition material between the chip and the heatsink?
Definitely.
In order to...
That's a really great question that you have asked. So yeah, you can do that, right? So if you want to just specify basically a thermal conductance, how you can simulate that is specifying a thermal conductance between two bodies where you have the connection, right? If I'm not wrong. So herein, let's say thermal grease is between heat sink and the chipset over here, right? You can select the joint over here, and from here you can just specify the thermal conductance. Right?
Oh, okay.
Just come in here, let me just drop the meshing, and you can define the thermal conductance that you have for the paste that you're applying or the grease that you're applying in between these two bodies.
Okay. And that's sort of like a thermal, some form of thermal, thermal resistance, essentially, is what you're applying there, right? So,
got it.
Yeah, and yeah, typically, just to answer, Antonio, that's a really good question. Usually, what I've seen from my experience is those thermal greases or pastes or transition materials will typically have some form of specced out thermal resistance or thermal conductance, and then you can apply that typically to that model between the two components. So I hope that answers your question for that application. Good question.
Yes, thank you so much.
No problem.
You're welcome.
Any other questions out there? That was a really good one related to the thermal transitional materials. Yeah.
So we have received a question from Chakraborty.
Yeah.
So could you please check in the chat section?
Yeah, you can have that kind of a simulation, Anirban. Yeah. So if you want to have two-phase of thermal simulation within Ansys Discovery, even pipes going around and those sort of things, you can have those sort of simulation within Ansys Discovery.
May I ask your friend, are you referring to two phases intermixing with each other or two mediums in the simulation?
I just meant a working fluid. So just a liquid state and vapor state of the same working fluid, not a mixture of two.
Oh, of the same working fluid.
Yeah.
Oh, so just the same working fluid. Oh, I don't know. Ali, do you know if I don't think we can do that with Discovery.
Yeah, I'm not sure on that, but I'll get back to you on this one offline.
What would be the application, or like what would be an application?
For example, cooling of MOSFETs or hot chips, like vapor chambers or heat pipes.
Vapor chamber, yeah, vapor. Yeah, heat pipes traditionally are modeled using general conduction value. You can use isotropic conduction values for heat pipes, but modeling the two-phase inside a heat pipe traditionally is not something that most thermal analysts will do. Using like I know what you're saying. Using two-phased vapor chambers that are non-heat pipe directly in contact with dye, which is typically what I've seen in more high-end military applications. Yes, we cannot do that type of analysis. I don't believe so, right, Ali?
Yeah, I just need to check it once.
Yeah,
but yeah.
We might be able to do that in refine. We might be able to do that in refine mode. We have to get back. We'll have to. Do you mind if we email you directly after the session to get you more information on that?
Sure, sounds good. I can share like some of the application we are looking at as well.
Okay. Yeah. Absolutely. Thanks for the question.
Yeah. Really good question. Thank you, Nirban, for the question.
Thermal transfer tapes and all that stuff. Yeah. Anything else out there? No? Okay. Well, thanks for joining. I hope as you've seen from the presentation that essentially what our whole objective is to do quick conceptual design so you can investigate different scenarios before you actually commit to a concept, kind of putting the power of simulation more in the designer's hands to be able to do some simple multi-physics feasibility studies. But I know right now there is no more questions on the floor, but if you guys want in the future, you're welcome to go on our website at futurescape.ca. You're actually welcome to try out the software yourselves. We actually encourage that because it's actually not too hard a software package to actually get started on. We can typically give you a 3-week trial. You can just go onto our website. You'll see at the top right, there's a section there that says free trial, and then you can just apply for a trial activation of the software. We'll be happy to help guide you with the installation and show you the training materials. Or better yet, if you like, Ali is one of our lead is the lead application engineer at our company. You're welcome to email him directly. So you can contact Ali. You'll see there's the his email there at the bottom left of the presentation. So you're welcome to take down that email. Just to let everyone know, we're going to be recording this webinar, and we will be emailing out the recording of the webinar to all of the participants along with the PowerPoint presentation. So we'll send out this PowerPoint presentation along with the video recording of the webinar. So you're welcome to share that with your teammate members. And also, you're welcome to contact Ali directly if you have any further technical questions post-meeting. Anyways, I just want to say thank you very much for attending. We really enjoy doing these webinars. If you guys have any other topics that you guys would like covered, it's really nice getting feedback from the audience on what other topics they would like to see. So please feel free to email us and let us know what you would like to see in future webinars. Thanks very much, and I hope you guys all have a nice day. Okay.
Thank you everyone for joining.
Thank you.
Thank you.